All right. Okay. Assalamualaikum and good day for everyone. Okay. Today we continue on module 1, single area OSPF version 2 concept. So you can get this from our e-learning, or also you can ask the representative lecturer. All right. Okay. Module 1, single area OSPF version 2 concept. Module objective. Module title, single area OSPF concept. So objective of this module, explain how single area OSPF operates in both point-to-point and broadcast multi-access network. So OSPF features and characteristic. First, we need to know how to describe basic OSPF features and also characteristic. OSPF packets describe the OSPF packet type used in single area OSPF. And operation for OSPF, explain how single operation single operation of single area OSPF operation. Yeah. Okay. Okay, OSPF features and characteristics. So introduction to OSPF. OSPF actually is a link state routing protocol, or one of the protocol that was developed as an alternative for the distant vector routing information. Distant routing information protocol, or RIP, used to RIP before. Okay, so means in Cisco devices used to operate, okay, using this RIP, routing information protocol. So OSPF has significant advantages over RIP in that it offers faster convergence and scale to much larger network implementations. So meaning that from RIP, they goes to this OSPF. Yeah. What is the OSPF? OSPF is a link state routing protocol that uses the concept of areas. A network administrator can divide the routing domain into distinct areas that help control routing, update traffic. A link is an interface on a router, a network segment that connects two routers, or a stub network such as Ethernet LAN that is connected to a single router. Information about the state of link is known as a link state. All link state information include the network prefix length, and also cost. This module cover basics of single area OSPF implementation and also configuration. So component of OSPF. All routing protocols share similar components. They all use routing protocol messages to exchange route information. Yeah. The messages help build data structures, which are then processed using a routing algorithm. Routers running OSPF exchange messages to convey routing information using 5 types of packets. First, hello packet. Second, database description packet. Third, link state request packet. Fourth, link state update packet. Fifth, link state acknowledgement packet. These packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the network, meaning the distance, current shortest path. Okay, that's the information that we need to know, okay, in order to choose the base route path. Yeah. Okay. So component of OSPF, we continue. OSPF messages are used to create and maintain three OSPF database as follow. First, adjacency database, which is we have a neighbor tables, okay, and then description of this database, list of all neighbor routers to which a router has established a bidirectional communication, one-to-one, yeah, bidirectional. This table is unique for each router, can be viewed using show IP or OSPF never command. Okay, when we type at the console, okay, show IP or OSPF never in order to get the information of agency database. Okay, all right. Second database, link state database, or we call the LSDP, short form for this. And the information of that we call topology table. So what are the topology tables? Topology table will consist of list information about all other routers in the in the network. The database represents the network LSDP. All routers within an area have identical LSDP. Can be viewed using show IP or OSPF database command. Okay, when you type this in the console, you can see the information of topology table or link state database. Okay, the third one, forwarding database. In here, there is information from this table, routing table. So at the content list of routes, yeah, generated within an algorithm is run to the link state database. So each router's routing table is unique and contains information on how and where to send packet to other routers. Finally, can be viewed using the show IP route command. And use this command so we can get information of routing table from this forwarding databases. Yeah. Okay. Continue on a component of OSPF. The router built the topology table using result of calculation based on Dijkstra shortest path first SPF algorithm. Okay, the SPF algorithm is based on cumulative cost to reach a destination. The SPF algorithm creates an SPF tree by placing each router at the root of the tree and calculating the shortest path to each node. Yeah, the SPF tree is then used to calculate the base routes. When SPF places the base route into the forwarding database, which is used to make the routing tables. Okay, this is the example, okay, of the scenario. So link state operation. To maintain routing information, OSPF routers complete a generic link state routing process to reach a state of convergence. The following are the link state routing steps that are completed by a router. First, establish neighbor adjacencies. Second, exchange link state advertisement. Third, build the link state database. Fourth, execute the SPF algorithm. Fifth, choose the best route. Yeah. Single area and multi-area OSPF. To make OSPF more efficient and scalable, OSPF supports hierarchical routing using areas. An OSPF area is a group of routers that share the same link state information in their LSDB. OSPF can be implemented in one of two ways as follow. One we call single area, second we call multi-area OSPF. For single area OSPF, all routers are in one area. Best practice is to use area 0. For multi-area OSPF, OSPF is implemented using multiple areas in a hierarchical fashion. All areas must connect to the bone area, which is area 0. Routers interconnecting the areas are referred to as area border routers, or ABR. The focus of this module is only single area OSPF version 2. So here is the example, all routers in one area. Okay, so we're using area 0. Multi-area OSPF. The hierarchical topology design options with multi-area OSPF can offer the following advantages. First, smaller routing tables, where tables are smaller because there are few routing table entries. This is because network addresses can be summarized between areas. Route summarization is not enabled by default. Secondly, reduce link state update overhead, meaning that designing multi-area OSPF with smaller areas minimize processing and memory requirement. Okay, so reduce overhead of exchanging the information. Third one, reduce frequency of SPF calculation. So in fact, from that also they can reduce the frequency of SPF calculation. Multi-area OSPF localize the impact of a topology change within an area. For instance, it minimizes routing update impact because LSA flooding stop at the area boundary. Okay, flooding means they will advertise to all the connected networks. Okay, so they can reduce also when we use this multi-area OSPF. All right, so version 3. So OSPF version 3 is the actually enhanced from the OSPF version 2. Basically, for version 3, actually they design for the exchanging IPv6 prefix. So OSPF version 3 exchanges routing information to populate the IPv6 routing table with remote prefix. Note with the OSPF version 3 address families feature, OSPF version 3 includes support for both IPv4 and IPv6. OSPF address families is beyond the scope of this curriculum. OSPF version 3 has the same functionality as OSPF version 2, but use IPv6 as the network layer transport communicating with OSPF version 3 peers and advertising IPv6 routes. OSPF version 3 also use the SPF algorithm as same as OSPF version 2 as the computation engine to determine the best path throughout the routing domain. So they still use the same algorithm from the previous version. Yeah. So OSPF version 3 has separate processors from its IPv4 counterpart. The processes and operations are basically the same as in IPv4 routing protocol, but run independently. Okay, that's the difference. OSPF packet. Okay, so this one is a video you can get from our website. Okay, you can see about this related packet. Okay, type of OSPF packet. The table summarizes the 5 different types of link state packet used by OSPF version 2. Okay, OSPF version 3 has similar packet type. So if you can see here, the first hello, for discover neighbors and build adjacencies between them. Second, database description, DBD, check for database synchronization between routers. Third one, link state request or LSR. Okay, request specific link state record from router to routers. Fourth, link state update or LSU, send specifically requested link state records. Fifth, link state acknowledgement, LSACK, acknowledges the other packet type. Okay, this is PI packet available in OSPF, either version 2 or version 3. Link state update. LSU are link state, okay, update. Link LSU are also used to forward OSPF routing update. And LSU packet can contain 11 different type of OSPF version 2 LSA. Yeah. OSPF version 3 renamed several of these LSA and also contains 2 additional LSA. All right. LSA, LSU, and LSA are often used interchangeably, but the correct hierarchy is LSU packet contain LSA messages. Okay, like this example. Hello packet. The OSPF type 1 packet is the hello packet. Hello packet are used to do the following: what? Discover OSPF neighbor and establish neighbor adjacencies. Second, advertise parameters on which two routers must agree to become neighbors. Third one, elect the designated routers or DR and backup designated router BDR on multi-access network like Ethernet. Point-to-point links do not require DR or BDR. Yeah. OSPF operation. So this video also you can get from our NetAcad website. Yeah. So you can see how this works in between all this OSPF operation. Okay, OSPF operational states. Okay, down state we have init state, which is initial state, two-way state. Okay, for down state mean no hello packet received, which is down. So router sends hello packet. Transition no init state. For init state, hello packet are received from neighbor. They contain the router ID of the sending router and transition to two-way state. In two-way state, in this state, communication between the two routers is bidirectional. On multi-access link, the router elect the BDR and also BDR. Transition to X state, X start state. Yeah. All right. Okay, X start state. On point-to-point network, the two routers decide which router will initiate the DBD packet exchange and decide upon the initial DBD packet sequence number. Okay, for next state, which is exchange state, means router exchange DBD packet. If additional router information is required, then transition to loading, otherwise transition to the full state. Next is a loading state. LSR and LSU are used to gain additional route information. Routes are processed using SPF algorithm. Transition to the full state. Okay, finally, full state, the link state database of the router is fully synchronized when it goes to the state. Yeah, which is, we call this full state. Establish neighbor adjacencies. To determine if there is an OSPF neighbor on the link, the router send a hello packet. Yeah. that contain its router ID out all OSPF-enabled interfaces. The hello packet is sent to the reserve all OSPF routers IPv4 multicast address 224.0.0.5. Only OSPF version 2 router will process this packet. The OSPF router ID is used by the OSPF process to uniquely identify each router in the OSPF area. A router ID in 32-bit number formatted like an IPv4 address and assigned to uniquely identify a router among OSPF peers. When a neighboring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. The routers used to establish adjacency on a multi-access network. Okay, down to initial or init state. When OSPF version 2 is enabled on the interface, R2 transitions from down to initial, and start sending OSPF version 2 hellos out of the interface in an attempt to discover neighbors. In initial state, when R2 receives a hello from the previously unknown router R1, it adds R1 router's ID to the neighbor list and respond with a hello packet containing its own router ID. So in two-way state, R1 receive R2 hello and notice that the message containing the R1 router ID in the list of R2 neighbors. R1 adds R2 router ID into the neighbor list and transition to the two-way state. If R1 and R2 are connected with a point-to-point link, they transition to X start. If R1 and R2 are connected over a common Ethernet network, the DR or BDR election occur. So the last process is elect the DR and also BDR. The DR and BDR election occurs when the router with the highest router ID or highest priority is selected as the designated router, and second highest is the BDR. Yeah, backup designated router. Synchronizing OSPF databases. After the two-way state, routers transition to database synchronization state. This is a three-step process, as you can see as the following here. Decide first router. The router with the highest router ID send it DBD first. Second, exchange DBD as many as needed to convey the database. The other router must acknowledge each DBD with the LSACK packet. Later send an LSR, so mean each router compares the DBD information with the local LSDB. If the DBD has more current link information, the router transition to the loading state. After all LSR have been exchanged and satisfied, the router are considered synchronized and in a full state. Update LSU are sent when a change is perceived or incremental update every 30 minutes. The need of DR. Multi-access can create two challenges for OSPF regarding the flood of LSA. First, creation of multiple adjacencies. Second, extensive flooding of LSA. Okay. The first challenge, Ethernet network could potentially interconnect many OSPF routers over a common link, creating adjacencies with every router would lead an excessive number of LSA exchange between routers on the same network. Second one, which is link state router. Link state router flood their LSA anytime OSPF is initialized, or when there is a change in the topology, the flood can become excessive. Okay, so this is the calculation. All right. Okay, LSA flooding with a DR. An increase in the number of routers on a multi-access network also increases the number of LSA exchange between the routers. The flooding of LSA significantly impact the operation of OSPF. If every routers in a multi-access network had to flood and acknowledge all received LSA to all other routers on the same multi-access network, the network traffic will become quite chaotic. On multi-access network, OSPF like what we call this DR to be the collection and distribution point for LSA send and receive. BDR is also elected in case the DR fail. All other routers become designated routers or DR. DR is a router that is neither DR nor the BDR. Sorry, D router. Sorry, DR other. Sorry, become DR other. DR other is a router that is neither DR nor the BDR. So net DR is also used with the dissemination of LSA. The router will still use the best next hop router indicate in the routing table for the following of the other packet. All right. Okay. That's all for module 1.